Hi everyone, greetings from Abu Dhabi. So a few weeks ago, I came across an interesting paper in Nature Astronomy about stellar flares and how it impacts exoplanetary atmospheres, their chemistry. And so I thought I should invite the lead author and give a talk. And so here we are. So I'm pleased to welcome Howard Chen from Northwestern University. He's a PhD candidate there. He is also a future investigator in NASA Earth, Space Science, and Technology. His research interests include planetary habitability, biosignatures, planetary atmospheres. So Howard, welcome, and I'm handing over the mic to you.
Thank you so much for the invite, and thank you very much for the introduction. I'm actually kind of sad I won't be able to visit Abu Dhabi in person, but I've never been to that area. But a few years ago, my undergraduate advisor, Jim Casting, was there, and he told me a lot of great stories about his visit there. So sounds like a great place to do science. So as Dimitra mentioned, I'm currently a finishing PhD candidate. And this paper represents kind of the culmination of what I've been doing throughout my PhD work. And one of the things that we wanted to look at was to investigate the time-dependent effects of stellar flares, because of my 2019 paper really focused on the time-averaged effects of stellar activity. But here we're looking at these problems in time-dependent sense. So this is kind of my hopefully not the final work, but really one of the, I think, represents a lot of what I've been working on throughout the 3 or 4 years or so since 2016. So I'd like to first acknowledge my co-authors, Allison, Zhu Chang, Eric, Adina, and Dan. They represent kind of, they all contribute a lot to the paper, and certainly this paper would not be, this project would not be a success without their contributions. So when we look up into the night sky, and I don't think you can do that here, I'm actually currently in Taipei, so it's actually a nighttime for me, but because of the light pollution here, and obviously because of COVID, I'm here back home, but you can't really see the night sky that clearly. But if you go out into the countryside, you can see night sky. And if you look at the night sky, as a kid, I grew up in a farm, and I typically wonder about what is out there. And now we know we live in a really exciting time, because now we know most of the stars in the galaxy, or by extension, the universe, have at least a planet orbiting it. The planet may not be habitable, but based on Kepler, we know that most stars have planets. At the heart of my PhD research, I try to answer the question of what are the nature of these planets? For instance, what are they made of? And what are their structure and their atmospheres like? This is really the dream. The dream is to image a planet and to figure out the detailed atmospheric composition. And obviously, this would hopefully, in a not too distant future, be done for very Earth-like planets. We can do this for gas giants and mini Neptune super Earths. But to do this for truly Earth-like planets would be a challenge for both instrumentation and computation. We typically decipher the atmosphere through transmission spectrum, which is transmission spectroscopy, which is measuring the starlight passing through the planet's atmosphere. And from there, we can really deduce what are the molecules that are being present on the planet's atmosphere. And from these spectrum, we can then decipher the specific climate conditions that this planet may have due to the different starlight passing through the planet's atmosphere. In the distant future, I want to remind everyone that these are more than points of light in the night sky, but worlds one day we may be able to venture to. That's something for me very exciting about exoplanets, because they are not just objects, but they're places that we one day may be able to travel to, but probably, unfortunately, not in any of our lifetimes. But still a very tantalizing thing to think about. One of the ways to measure the existence of exoplanets is to look at the shift in the planet's motion that's tugging from the star. We can deduce it from the star. We don't measure the planet. We can't see the planet, but we can indirectly measure the properties of the planet. For instance, here, the planet mass, by the motion of the star. So when a star is moving away from us, it's rev shifted. When a star is moving towards us, it's blue shifted. By far, the most common method is the transit method, which measures the dips in stellar brightness, which can provide us constraints on the planet radius. So together with the radial velocity or stellar wobble technique and the transit method, we can convolve these two and provide us a handle on the planet density. So why is planet density, the bulk density, important? Because from there, we can infer the bulk composition of the planet that in question. And this is a very common method to, if we can simultaneously get the planet mass and the planet radius, we can get a sense of what the planet might be made of. And Zhang et al. Has compiled these beautiful mass-radius relationships that shows if we can get some understanding of both mass and radius, the mass doesn't necessarily have to come from radial velocity, but it's a very common way. Other methods are such as transit timing variations and other methods that can give us a handle on the planet mass. But this is a kind of the thing that we need to get right. Radius is pretty common due to the transit method being such a popular technique. So, but if we can get the planet mass, we can understand something about the planet bulk composition. And most of the planets, as you can see here, discovered, I'm not sure you can see my cursor, but most of the planets discovered by Kepler and since Kepler has been these super Earth-sized planets that we don't really see in the solar system. They're with radius between and mass between Earth and Neptune. This is by far the most common types of planets found by Kepler. So we do have relatively good handle on their mass constraints. Obviously, the uncertainty is still pretty big, but one of the most biggest mysteries for me going to my PhD is thinking about their atmospheres and what their atmospheres might be made of. This is because soon we will need to use these very precise models to help us both predict and interpret future observations to retrieve planetary characteristics. This is both for transmission methods and direct imaging methods that proposed missions such as HAPAX and LUVAR can give us better insights on the atmospheric compositions of truly Earth-sized planets. But also I want to mention that a lot of ground-based observatories, such as the Extremely Large Telescope, are being developed that can have very high-resolution spectrographs that can image potentially super Earths, maybe not truly terrestrial planets, but probably pushing to Earth radius, which is still pretty tantalizing. Well, so what does atmospheric characterization involve? Well, it breaks down to understanding their composition, their chemistry, and the role of clouds. Clouds are really common based on observations of various types of planets, most specifically super Earth-sized planets. Clouds play a huge role in not only photochemistry of the planet, but also it highly affects observations. It can mute spectral features of various biogenic or just abiotic compounds that we want to characterize. So understanding these three effects are very important. The type of planet that I'm particularly interested in are planets orbiting the habitable zones of these host stars. And here, showing here is a cartoon of the host star spectrotype as a function of the stellar insolation, ranging from greenhouse climates to icehouse climate. This is bracketed by the inner edge and the outer edge of the habitable zone. 30 years ago, these are the 3 known habitable zone planets. And we have begun really living in a very exciting time because we have begun to populate the known number of habitable zone planets since the discovery of the first exoplanet, really. We have been pushing our limits and discover more and more habitable zone planets that orbit FGK and M stars. My focus, at least for the past 2 projects I've been involved in, are planets orbiting K and M dwarfs. There are many reasons to look at K and M dwarfs. For instance, the high transit frequency, the lower star-to-planet brightness contrast. There's another reason why M dwarfs are very important, a reason that people don't really appreciate. And if we go to the observatory, go to any observatory nearby, near your home, most of them have this kind of image showing the main sequence of various types of stars. And tucked away in the corner are these K and M dwarf stars. But actually, K and M dwarfs make up most of the stars in the Milky Way and potentially the universe. So that's a very important fact, that most of the stars are M dwarfs. And that's kind of a very profound thing, because this means that whatever is true of planets around M dwarfs, whatever we find out to be true of planets around M dwarfs, should then be true. This fact should then be true for most planets in the universe. There are many problems to consider habitability for planets around M dwarfs. One of them is that M dwarfs are very active in the high energy radiation regime. Not only that, their lower brightness means that the planet must be closer in to receive the same amount of stellar insolation to have liquid water to be persistent on the surface. For instance, in the Kepler 186f system, we see that Kepler 186f must be much closer in towards the host star compared to the Earth. So this means that the changes in the luminosity or the high energy radiation fluxes from the host star would be amplified due to simply the inverse square law, the fact that the planet is so much closer in compared to the Earth. One very kind of interesting finding for people who are looking at the M dwarfs, and this is a very nice observation by Hawley and Peterson in 1999. These great AD Leo flares that they have discovered turns out to be actually quite common for M dwarfs. They frequently exhibit typically monthly to even weekly, quote unquote, great AD Leo flares. And if you compare that to the largest solar flare ever observed or ever recorded, is the Carrington event in the 1800s. It's only about 10 to the 31 ergs. That's a total 3 orders of magnitude difference in the flare energy. But again, this is comparing the common flare that we can see, pretty common flare, to the largest solar flare. So that's important to keep in mind. So if we can kind of step back a little bit and answer the question of what are stellar flares? Well, it depends on who you ask. If you just Google stellar flares, this is what you get. But this is not what we're going to discuss today. What we're going to discuss are these type of flares, right? And these typically involve sudden changes in the magnetic activity from the host star, and comes from this process known as magnetic reconnection, which is basically changes in the current in the photosphere or corona or chromosphere can induce changes in the kinetic energy and result in the release of kinetic energy from thermal energy. So these high energy releases from the host star can affect atmospheres in various ways. One of the ways that is pretty well known, since we have satellites up on Earth's orbit, is the effects of ozone. Ozone is important that the government really cares about it because it affects not only surface pollution, but affects how much UV radiation can be penetrated to the surface. So this is something that we've been monitoring on Earth for a long time. And we expect, even though the effects of ozone for solar flares aren't very large, we expect them to be much bigger, again, simply due to the highly energetic activity on M dwarfs. Ozone is important because it filters out UVC and UVB radiation. These higher energy UV radiation can damage surface life. So again, just kind of summarizing what are stellar flares, they really originate from the interaction between the photosphere, the corona, and the magnetic field, and this comes from this magnetic reconnection event that converts the kinetic energy, converts the magnetic energy to the release of plasma kinetic energy. So apart from the stellar magnetic activity or magnetic field, the magnetic field of the attendant planet is also very important. And this is something we've been thinking about in our study, which is how magnetized or could exoplanets be? And this is tied to the planet rotation. For a rapidly rotating planet like the Earth, the magnetic field is pretty strong. And this kind of induces a strong magnetosphere, which can deflect and redirect incoming charged particles from solar wind and solar flares to the poles. So on the Earth, again, I kind of alluded that earlier, it doesn't do much to the ozone. It does affect it by a little bit, but by a very small percentage. Most of the effect is seen here at beautiful Aurora Borealis. It's a pretty kind of sight that we only see at poles. This is because of the ionized charged particles that's interacting with the upper atmosphere. So the particles coming from solar activity doesn't really affect us who are living on the surface of the Earth. It affects the space weather, but not really the surface or really the bulk atmosphere. However, for tidally locked planets, for a planet that does not have a strong magnetic field, most of the charged particles get directly deposited to the day side hemisphere, just simply due to the lack of a magnetosphere. And this can be seen where it's evidenced by our solar system's past. Mars lacks a strong magnetic field, so its atmosphere is believed to be eroded early on by the solar wind, even though solar wind is not even that strong comparatively. Whereas here on Earth, we have the magnetic field creating a magnetosphere that acts as a shield for any strong charged particles coming from the host star. And this makes people think that the existence of a planetary scale magnetic field could be one very important factor for having a habitable environment. This is controversial because there are other people who think that magnetic field doesn't really help, because if you really can look at the escape rate, the present escape rate of ionic species for Earth, Mars, and Venus, there really isn't a big difference. So again, this is a controversial thing, but it could help. So in our study, we take flare data from the TESS survey, as well as the Hubble Space Telescope campaign, and we use a machine learning algorithm to identify the existence of flares. This is done by Adina Feinstein, who is a grad student at University of Chicago. And we took these data and used them as input to a three-dimensional high-top coupled chemistry climate model. This is a model that's published in my 2019 paper. If you're interested, I have a link in the end of this talk that you can go check out. And finally, we take the outputs from this CCM and use them as inputs to another model, which is the radio transfer atmospheric spectroscopy code. This is developed a modification of the Seeger et al. Radio transfer model that's being used by the group at MIT. And this is used to look at the effects of flares on the transit spectrum, the transit transmission spectrum that we might be able to observe with instruments such as James Webb Space Telescope. So I'm really happy to tell you all that this paper was finally published. At the end, we got the very last kind of last week of NetAstro's kind of publication schedule. So I was very fortunate that I was able to publish in 2020, and it represents kind of a year to 2 year long work since my 2019 paper. So again, I have a link at the end of this talk. If you're interested in this paper, you can check it out, or can you email me for a free copy that Nature has provided us. So I'm going to kind of jump into the results now. But before I do that, I want to quickly kind of go over one critical point, which is how do we get the particle fluxes from the host star? Because all of you know that we only observe we observe light, which is basically photons. So how do we get measurements from charged particles that are associated with coronal mass ejections and flares? Well, we have to use or have to rely on solar proxies. This is a well-known relationship between the X-ray intensity and the proton flux. And again, this is unfortunate because this is kind of a very big caveat in our study, because the direct measurement or direct measurements of M-dwarf's energetic particle emissions are just currently not possible. There are ways to guess or make guesstimates of the energetic particle fluence for a given event, but those are mostly spurious, and there are a lot of issues with those methods. So we rely on a solar proxy here instead. So that's a really big caveat before I jump into the results. So showing here is the mixing ratio of various chemical reservoirs as a function of time. On the upper panel is the mixing ratio of these gases, and the panel below is the input proton fluence. And basically, if you can think of the large fluences, large events, as a strong flare. So showing here is a magnetized planet around a sun-like star first. So as you can probably tell, when there's a large flare, the NO increases, nitric oxide, OH also increases, and ozone is dropped by kind of a small amount, kind of not really noticeable in many of these cases. And this is because the planet is magnetized. So the stellar protons here are redirected to the poles by the magnetic field. And showing here is the NO global distribution time slice of nitric oxide. It is produced via interaction between molecular oxygen and its associated component or excited state of nitrogen. It also interacts with the ground state of atomic nitrogen as well. What about ozone? So ozone is important. I guess one of the things that we really care about, because not only does it protect life, but also it has a prominent signal, it's 9.6 micron in transmission spectrum. So it could be prominently observed, and people think of ways that we might be able to simultaneously measure ozone and reduce gas such as methane. So understanding changes in ozone is very important as well. Here, the change is very small. So 30% is not big in terms of observations, right? So, and again, this is going back to the fact that these planets are magnetized. But what about an unmagnetized planet? What about planets around K and M dwarfs? Well, in this case, I alluded to earlier that these planets experience direct day-side interaction with the incident UV radiation and charged particles, including protons and alpha particles. So here I'm showing the OH hydroxyl radical concentration at different time slices. And you can see that most of the OH is produced on the day side and slowly decays with time. And showing here is the similar time series for these important gases. As you can see, instead of this oscillating behavior in which the chemical reservoir concentrations quickly return to the pre-flare state, the chemical reservoir concentrations deviate away or depart away from the pre-flare state with time, with repeated flares. Again, we can kind of put it side by side to have a better comparison. On the bottom is a planet around a G dwarf, and the top is a planet around a K dwarf. So you can see that the behavior is quite different given the same flare input. And that's very important. I forgot to mention that the input flares that we inject are the same, but due to the different properties of the planet, the effects is significantly different. The stellar spectrum, the stellar spectral energy distribution would play a role as well, but might not be that big of a role. So for planet around a KM dwarf, we see rapid ozone destruction, not unsurprisingly, whereas here, the ozone really isn't that affected. So we can have a better view of what's happening if we look at the vertical profiles of ozone at different stages of the stellar activity. We can see the main, which is kind of the main flare that we're discussing in our paper. It's a main instead. It has a flare of proton fluence of 10 to the 24.5 protons per centimeter squared. So that's kind of our definition of main. And you can kind of refer to our paper and what we mean by that. Active is just a bit higher, I think a 2 orders of magnitude higher than that. Quiescent is just lower. So we do see that for the active case, the total ozone column is significantly reduced. And this follow-up work would be to understand or examine the surface UV flux that experienced by the planet with lesser ozone compared to the planet with more ozone. One interesting thing that we found, if we look at cases that are oxygen poor and planets that are in a state of moist greenhouse, all these results I've shown, all these results are oxygen rich. So if we move to alternative atmospheric compositions, we see some very interesting results. One of them I want to show here, bear with me a little bit, but this might be a little bit confusing, but I want to go through what we did here. So if we look at a O2 poor planet, which is throughout Earth's history, the oxygen concentration has significantly varied with time. So we look at the Proterozoic, the O2 was just 1 or 0.5 to 1% of present Earth's. If we look at that case, the nitric oxide for pre-flare states, which are the blue, the pre-flare state NO is very low, as you can see here, because of the O2 with the poor O2 concentration. But if we inject a flare, or if the planet is we're experiencing repeated flares, both NO vertical profile concentrations approach one another. Whereas again, before the flare, it is significantly different, or different by orders of magnitude. So that's very interesting. That means that in cases that O2 might be difficult to detect, we can instead look at NO, and that might give us a signal that there is O2. If we run a simulation without any O2, there would be, NO would not vary like this, because NO again comes from, I showed the equation here, reaction between O2 and excited state of atomic nitrogen. So without O2, you have even lower NO. For the case with a planet experiencing moist greenhouse, which is a planet that has most of its stratosphere with upper atmosphere saturated with water, this is believed that to be what happened with Venus. And if the planet is saturated, upper atmosphere is saturated with water, the water would experience photodissociation, and the hydrogen would escape, and the O2 will quickly react with chemical compounds on the surface. So that's what that's what people think happened to Venus. If we look at a moist greenhouse atmosphere, it's basically positioning the planet closer into the host star to create this condition. We can see that comparing the temperate here defined as a dry upper atmosphere, which is currently what Earth is experiencing. If we compare a dry stratosphere to a wet stratosphere, we can see that flares actually push planets that are initially dry to a very moist state. So this means that people, if we kind of and this is important because moist greenhouse can be used as the delineation of the inner edge of the habitable zone. But showing here is that flares can also push planets that are traditionally outside or beyond the optimistic habitable zone, could also be pushed to this or towards this moist greenhouse state. So that's very important to keep in mind that most of the habitable zone publications out there neglect this kind of effect that could alter the atmospheric composition and has subsequent implications for the escape of various chemical reservoirs, such as water vapor in this case. The other effect that people, past studies, including one-dimensional work, has neglect is the atmospheric transport of chemical constituents. So this is showing here is the concentration as a function of pressure and time for nitric oxide. For a planet around a K-dwarf and a planet around G-dwarf. So in this case, it's slow rotation. In this case, is rapid rotation. As you can probably see, when there's a flare, you get a lot of nitric oxide. For a planet with rapid rotation, you get downward transport of the chemical constituents. This is due to the effects of eddies and the effects of turbulence. For a slow rotation, slowly rotating planet, you don't really get that effect. Most of the chemical constituents, in this case nitric oxide, is produced via a flare, stays in the upper atmosphere. And this is due to, again, the rotation rate of a planet. So the atmospheric circulation is also very important to determine how chemical constituents can be transported. And this is important, obviously, because if you get to the lower atmosphere, it might react more dramatically with things like ozone, which are more concentrated in the stratosphere, as opposed to the very, very upper atmosphere. The ozone abundance is quite low. So people have proposed, this is not, we didn't do this, but people have thought about via hypotheses or perspective papers, thinking about how can we use these constituents that are produced by flares as a proxy for the existence of life or a habitable environment on the surface. On Earth, we can see that the anode abundance is increased by a factor of 10. In our studies, more like 100, because we have planets without magnetic field. For the Earth, this increased by a factor of 10. It's actually quite important for detection, because obviously our satellites are much closer in. But are there other beacons of life that we can think about that are produced by time-dependent stellar activity that we can leverage for detection? And one of the things I want to think about in my final paper, my PhD, hopefully, is ionized oxygen. And I don't want to spoil our work, but just want to say that ionized oxygen is only present if you have abundant O2. And Venus and Mars don't have abundant O2, and thus abundant ionized oxygen, or O+. So these are something that are produced by stellar activity and are things that we can start thinking about alternatively or concurrently with traditional or canonical biosignatures such as O2, CH4, and N2O. So I kind of mentioned in the methodology slides that we're ultimately interested in observations, right? Because habitability is important, but we don't know. There are extremophiles that can withstand a lot of UV. So that part of it's ultimately uncertain in terms of how much ozone a planet needs to have a traditional habitable environment. But if we look at observations, so we can think about the constituents that are affected by flares. And here I'm showing the nitrogen oxide reservoirs, various of them, including nitric oxide, nitrogen dioxide, and nitrous oxide, which is NO, N2O, and NO2, as well as HNO3. It's not strictly a nitrogen oxide, but it's still something that could be prominently highlighted during a flare. So this is the red curve designate the atmosphere experiencing flares, and the blue curve designates the planet that does not have flares, or did not receive any flares throughout its chemical evolution. Unfortunately, these signals are quite low and probably not discernible by near future instruments such as James Webb, but it could be verified with instruments in the future with better noise floor control. This is my current work to look at the ionization of various planet atmospheres. In this study, we focus on the chemistry part of things, so we limit ourselves to incident stellar fluxes longer than 120 nanometers. So we don't really deal with anything below 110 nanometers. So that regime brackets the X-ray and EUV fluxes. X-ray and EUV fluxes can ionize various chemical reservoirs. In this case, the majority of them are things like nitrogen and oxygen and water vapor. And our current work looking at the UV-driven ionospheres or ionosphere compositions of planets around M dwarfs. It's kind of preliminary simulation, so it does not represent the final result. But if we include the effects of flares that we mentioned in this talk, and incorporating the effects of extreme ultraviolet and X-ray, we can get a sense of what the ionosphere composition would be like. And we find that this is by no means new. This is what people have looked at for planets around M dwarfs, and they found that these planets are not the best candidates for traditional surface life because the high mean molecular species can easily be driven out by this strong EUV flux. So for this case, for Proxima Centauri b, it is probably difficult to withstand a persistent atmosphere. So that's something that we found that people have already reported. But what we can do here, if we can actually map out the specific ionosphere composition of the entire ionosphere. Most studies only look at the upper part of the ionosphere, the part that's important to escape. In this case, because we have a climate model, we can actually simulate the Earth or planet system. So we can get a better constraint of what the ionospheres might be like for these exoplanets. Venus also has experienced significant atmospheric escape. And we have started, obviously, you all know about the new Venus news that appeared a few months ago, but there is a renewed interest in Venus. And one of the things that we want to apply a model to is to instead look at Venus-like exoplanets that have CO2-rich atmospheres, because these planets are not just might be common, but they might be orbiting closer into the host star and thus enhancing the prospects of detection or atmospheric characterization. So this is something that we're currently working on, and stay tuned. Hopefully I can get something out before I finish my PhD. And something that I want to look at, not just me, but as a community, as part of kind of the exoplanet modeling or exoplanet habitability community, something I've been trying to look at is to incorporate or expand the number of chemical or atmospheric composition that we can investigate. Obviously, here we're restricted to Earth-like nitrogen-dominated atmosphere, but there's no way, planets, any exoplanet would be exactly the same as the Earth. There's so many of them. So to develop and explore exoplanet models with non-Earth-like planets or non-Earth-like conditions is extremely crucial, and something I will try to work on, hopefully after I finish my PhD or my dissertation. And we want to kind of integrate, create libraries of spectra or predictions that can better inform the observations of future instruments. They're very exciting because a lot of them coming online. The nearest one is James Webb, that can hopefully improve our understanding of what the atmospheric compositions are like as it impacts by the host star. So I would have to not just get better planet spectra, which we hope to, but the importance of getting better stellar spectra is extremely important. So my work really relies on observers to get better and better and more precise observations of different types of stars. And finally, I want to kind of conclude with a few takeaway points, and hopefully we have time for questions. So one of the things that we discovered is that in this paper that time-dependent stellar activity can generate secular changes in various chemical reservoirs, most significantly on unmagnetized planets. In some cases, flares can highlight the existence of oxygen, even for, this is a typo here, but even for O2 poor compositions. They can also push the upper atmosphere into a moist greenhouse states, which is important because moist greenhouse typically represent the inner edge of the habitable zone, as a planet that goes into this state could rapidly experience the loss of hydrogen in geological significant timescales. So planets are initially temperate, may not have abundant surface water if they experience repeating flares. And lastly, flares can drive changes in atmospheric features in transmission spectrum, such as those of N2O and NO2, and are potentially detectable by JWST, but unlikely. And I'll leave you with the citation or links of a few of my papers. And thank you all for your time, and I'm happy to take any questions you may have.
Right. Thank you, Howard. That was a great talk. Now we are
Thanks
open
for that.
for questions.
Maybe I'll ask one to get started.
Okay.
Can you thank you again for the very interesting talk, and congratulations on your papers and your work.
Thank you.
Can you briefly state the essential ingredients of your 3D model? I mean, it looks pretty complicated to me. So maybe just tell us what are the major aspects of it.
So the 3D model comes from it's really an Earth heritage model. It was originally developed for Earth-based research, and we took it basically out of the box, and then we started changing some of the codes. And most of the changes that has been performed on this climate model is done on an online. It's publicly available. The modules are publicly available. It's by Eric Wolf. His ExoCam modifications really helped me in adapting my three-dimensional climate model to better suit it to simulate exoplanets. In terms of the key features, it's really a coupled model. So what's important is that atmospheric circulation and atmospheric chemistry can interact with one another. So this is really the state of the art, even for Earth. These sort of models are only been used recently for climate, mainly for climate projections, to project future climate. So these are really the state-of-the-art kind of models that Earth scientists have been using, or atmospheric science, climate scientists have been using, and we have just introduced it to the exoplanet community. And one of the things that's important, not just for the Earth, but well, maybe less so for the Earth, but one of the things that it can include is photochemistry and photodissociation effects that most general circulation models don't consider. So we can begin to analyze the effects of star-planet interaction with this quote unquote new code. I do want to talk about, I can talk about the advantages for days, but I do want to talk about a lot of the downsides, because one of the downsides of this code is that it's really Earth tuned, because it's so complex. It has chemistry, dynamics, ionization, ion chemistry, and stuff like that. It's really tuned to the Earth. So a lot of work is acquired to really adapt it better for exoplanets. I mentioned here that I want to change the chemical modules for it to better suit it to work for non-Earth-like atmospheres. And that's kind of my proposed postdoc work. For instance, looking at reduced conditions or anoxic conditions that might be even more common for exoplanet, for the eventual state of many exoplanet evolution. So adapting not just the inputs, but also some of the hard-coded routines and modules within this climate model is a challenge. And that's something that I hope to improve in the near future.
Perhaps as a small follow-up, the atmospheric models that are used in the Earth's context really depend very specifically on the fluid dynamics of the specific fluid dynamics of the Earth, right? I mean,
yeah.
So translating them to another exoplanet might be very uncertain, is it not? Or am I missing something?
Fluid dynamics of the Earth, you mean like it's dictated by the Earth's atmospheric circulation, or?
Yeah. For instance, yeah, its topography, it's the wave structure in the atmosphere, all of that. But I understood the point you made about the interaction between the chemistry and the dynamics. Yeah.
Well, in terms of fluid dynamics, I don't think that's that difficult of a problem. Like most general circulation models or global climate models that people call it already looked at those. I mean, the most important factor is the insulation drives circulation, the heat distribution drives circulation, but also by far the most important factor is the rotation rate of the planet. Small changes in rotation rate can affect the circulation pattern. So people have looked at that for a while in terms of 3D climate models. My collaborators, Ravi Kebrapu of NASA Goddard and Eric T. Wolf at UCU Boulder have looked at those for a few years. But you're right that if we want to consider other planet-specific things, such as the topography, how that can affect the fluid dynamics, it's something that's more uncertain. But in terms of getting the general idea of, the planet's circulation pattern, I don't think that's that difficult.
Yeah. Okay. Thank you.
Problem.
Yeah, we have another question. Ian, go ahead.
Yeah, Ian has a question.
Oh, sorry, I didn't realize I could actually speak. That's good. I just wanted to build on Sri's question a bit and just asked about basically how the dynamics carries the non-equilibrium chemistry throughout the atmosphere. So I don't know, from the pole where it can actually occur to the equator and so on and so forth. So comparing the meridional timescale or the zonal timescale to the chemical timescale. I mean, imagine the chemical timescale is rather short here. So are you going to get something that's observationally different if you turned off the dynamics, for example?
Yeah, so that's a very important question. Actually, my 2018 paper says no. I mean, the dynamics is important because it could affect it's just, if you look at the mean state of a planet's chemistry, if we consider like 100-year integrated simulation, if we include dynamics versus not, the difference is probably 20 to 30% difference.
Okay.
So in that sense is not, I mean, for observations your question is not just if you get different, but something that's testable, right? That's different, but that's testable. That difference could be testable. And the answer is no. The answer is probably not. And we didn't write that explicitly in our 2018 paper, but that's what we found. But
this is in contrast to maybe like to larger planets with thicker atmospheres where the chemical timescale could increase significantly.
Yeah, precisely. Yeah. For Earth-sized planets, the difference is not that big. But yeah, but that's just comparing one-to-one. If we don't have dynamics, let's just say one-dimensional model with just vertical diffusion versus a large-scale dynamics like a three-dimensional climate model. The chemical, the equilibrium chemistry isn't that different in terms of observations. I don't think we will have to worry about. I think one-dimensional models in terms of just doing chemistry is fine. But again, the problem comes from if we want to consider things like magnetic field or whether the planet has a magnetic field and stuff like that. That's where you need a three-dimensional model.
Okay, thanks.
Thank you.
Any other questions? Please, you can raise your hand, use the Q&A feature, put it in the chat box. If not, then let us thank the speaker. Thank you, Howard. And
thank you so much.
Thank you, Howard.
Next week.
Thank you.
Come and visit us some other time.
Of course.